Imagine discovering something so bizarre in our solar system that every time scientists point a telescope at it, it breaks another law of physics we thought was unshakable. I'm not talking about some distant galaxy billions of light years away. I'm talking about something that passed through our cosmic neighborhood just recently, something we could actually observe up close. In August 2024, amateur astronomer Christopher Jacques spotted a faint smudge of light moving through the constellation of Lyra. Within weeks, this discovery would become what Dr. Matthew Knight from the Naval Research Laboratory called the most perplexing visitor from interstellar space we've ever encountered. Its name? 3I Atlas. The 3I means it's only the third confirmed interstellar object ever detected by humanity. Here's what will blow your mind. ʻOumuamua, our first interstellar visitor in 2017, was strange. Borisov, the second one in 2019, was weird, but at least behaved like a comet. But 3I Atlas? It's doing things that make theoretical physicists question their own calculations. It's changing brightness in patterns that shouldn't be possible. It's accelerating when it should be slowing down. And its chemical composition? It's made of materials that challenge our understanding of how stars and planets form. What if I told you that the more data we collect on this object, the less sense it makes? That every answer we find generates 10 more questions that are even more disturbing. Before we dive into this cosmic mystery that's keeping astronomers awake at night, smash that like button and subscribe, because this is going to get wild. And drop a comment telling me which country you're watching from and what time it is there right now. I'm curious how far across the globe this story is reaching. Are you watching this during your morning coffee in Tokyo? On your lunch break in Berlin? During a late-night research session in São Paulo? Let me know. Let's start with the basics, but I promise you, even the basics of 3I Atlas are mind-bending. When we say something is interstellar, we mean it didn't form in our solar system. Think of it like this. Imagine you've lived your entire life in a small town, and everyone you know was born there. Their parents were born there. Their grandparents were born there. Then one day, a stranger walks into town speaking a language nobody recognizes, wearing clothes made from materials that don't exist locally, carrying tools that use technology your town hasn't invented yet. That's essentially what an interstellar object is. It's a cosmic stranger from a completely different stellar neighborhood. Our solar system is like an island in a vast ocean of space. We have our sun, our planets, our asteroids and comets. They're all family members who formed together about 4.6 billion years ago from the same cloud of gas and dust. They orbit the sun because gravity is keeping them tied to our stellar home. But space between star systems isn't actually empty. There are rogue planets, ancient comets, chunks of rock, and who knows what else floating through the darkness between stars, untethered to any sun, drifting for millions or even billions of years. Now here's where it gets interesting. These objects are moving incredibly fast relative to our solar system. We're talking about speeds of 50,000, 100,000 miles per hour or more. At those velocities, they zip through our cosmic neighborhood relatively quickly. This is why detecting them is so rare and so exciting. It's like trying to photograph a bullet as it flies past your window in the dark. Dr. Koren Meach from the University of Hawaii, who led the team studying ʻOumuamua, explained it this way. Before 2017, interstellar objects were purely theoretical. We knew they had to exist based on our models of planetary formation, but we'd never actually seen one. Now we've seen 3 in just 7 years, and each one is rewriting what we thought we knew. 3I Atlas was discovered on August 11, 2024, by the Atlas Survey System in Brazil. That's the Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to spot potentially dangerous asteroids. Christopher Jacques was reviewing the automated detection data when he noticed something unusual. The object was moving wrong. It wasn't following a typical elliptical orbit around the sun. Instead, Its trajectory was hyperbolic, meaning it was moving so fast that the sun's gravity couldn't capture it. It was just passing through, like a cosmic hitchhiker, hitching a brief glimpse of our solar system before heading back out into the infinite darkness. But here's the twist that should make your brain tingle. When astronomers calculated 3I Atlas's velocity and trajectory backward, tracing where it came from, they couldn't identify a clear origin point. With ʻOumuamua, scientists eventually traced its path back toward the constellation Lyra, and possibly the star WISE 08550714. With Borisov, its chemistry suggested it formed in a system with a red dwarf star. But 3I Atlas? Its trajectory suggests it's been wandering through interstellar space for potentially hundreds of millions of years, long enough that its original star system could have moved significantly or even died. Think of it like trying to trace the origin of a message in a bottle that's been floating in the ocean for a century. The currents have changed, the coastlines have shifted, and the bottle itself has been worn smooth by time and water until you can't even read the original writing anymore. Dr. Davide Farnokia from NASA's Jet Propulsion Laboratory ran the orbital calculations and said something that sent chills through the astronomical community. 3I Atlas's orbit suggests it's encountered multiple stellar systems during its journey. The gravitational perturbations we're seeing in its trajectory are consistent with an object that's been pinballed through space, potentially for longer than complex life has existed on Earth. Let that sink in for a moment. This object may have been traveling through space since before the Cambrian explosion, when the most complex life on Earth was basically just weird ocean worms and early arthropods. It's older than trees. It's older than fish. It's been sailing through the cosmos, silent and alone, for an incomprehensible span of time. Now that you understand what 3I Atlas is and where it came from, or rather, where we think it came from, let's talk about the first thing that made astronomers realize this wasn't just another space rock. Let's talk about its light. When you observe any object in space, you're really just collecting photons, particles of light that have traveled from that object to your telescope. The way those photons behave tells you almost everything about the object. How bright is it? That tells you about its size and surface properties. What color is it? That reveals its chemical composition. Does its brightness change? That can tell you if it's rotating, if it has an irregular shape, or if something on its surface is reflecting light differently. Here's what should happen with a normal asteroid or comet. As it rotates, different sides face the sun and your telescope. If it's irregularly shaped, like a potato or a cigar, you should see a regular, predictable pattern of brightness changes. Bright when the long side faces you, dim when the short side faces you. This pattern is called a light curve, and it's one of the most basic tools in astronomy. 3I Atlas's light curve is absolutely bonkers. Dr. Yanga R. Fernandez from the University of Central Florida was one of the first to notice something deeply wrong. In September 2024, his team pointed the Gemini Observatory's telescope at 3I Atlas and collected data over a period of 6 hours. What they expected to see was a smooth, periodic variation in brightness, maybe getting brighter and dimmer every few hours as the object rotated. What they actually saw was chaos. The brightness fluctuated wildly and unpredictably. Sometimes it would dim by 40% in just 20 minutes, then brighten again just as quickly. Other times, it would remain stable for an hour before suddenly spiking to twice its previous brightness. The pattern, if you could even call it a pattern, didn't repeat. It was like watching a light bulb flicker randomly, except this light bulb was hundreds of millions of miles away and not connected to any electrical system. Here's what will blow your mind. This shouldn't be physically possible for a solid object. Rotation rates are stable because of conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in. An asteroid can't just randomly speed up and slow down its rotation without some external force acting on it. And there was nothing near 3I Atlas that could be causing these changes. Dr. Fernandez published his findings in October 2024, and his conclusion was startling. Either 3I Atlas has an extremely complex, irregular shape unlike anything we've encountered, or something on its surface is actively changing its reflective properties on timescales of minutes to hours. Both possibilities are deeply troubling for our current models. Think of it like this. Imagine you're watching a rock tumbling down a hill. You can predict how it will move based on its shape, its weight, and the slope of the hill. Now imagine that rock suddenly starts tumbling faster without any apparent reason, then stops, then starts again, then tumbles sideways for a while. That's basically what 3I Atlas is doing with its light. But it gets weirder. When astronomers analyzed the color of the light coming from 3I Atlas using spectroscopy, a technique that splits light into its component wavelengths like a prism creating a rainbow, they found something that made no sense. The spectrum kept changing. On September 15, 2024, the object appeared relatively blue, suggesting a surface composition rich in certain minerals or ices. On September 22nd, just 1 week later, it appeared distinctly redder. By October 3rd, it had shifted back toward blue again. This is like watching a rock change from granite to sandstone, to marble, and back to granite over the course of a few weeks. Dr. Alan Fitzsimmons from Queen's University Belfast, who's been studying comets and asteroids for over 30 years, said something in a press conference that captured the scientific community's confusion. In my entire career, I've never seen anything like this. Surfaces don't just change color on these timescales without some active process. But we can't identify what that process might be. Before we go further, let me ask you something that's going to seem relevant very soon. What if the reason 3I Atlas's light behaves so strangely isn't because of what it is, but because of what's happening to it right now, in real time, as it passes through our solar system? What if we're watching something transform before our eyes? Hold that thought, because the chemical analysis is about to make this mystery exponentially more disturbing. But first, if you're enjoying this deep dive into one of the most baffling objects in space, take a second to hit that like button and make sure you're subscribed with notifications on. This story is developing as we speak, and I'll be updating you as new data comes in. Let's talk about how stars and planets form, because understanding that process is essential to grasping why 3I Atlas's chemistry is so disturbing. When a new star is born, it forms from a massive cloud of gas and dust called a molecular cloud. The cloud collapses under its own gravity, and as it spins, it flattens into a disk. The center of that disk gets hot and dense enough to ignite nuclear fusion. Congratulations, you've got a baby star. But there's still a lot of leftover material in the disk, and that material gradually clumps together through collisions and gravitational attraction to form planets, asteroids, and comets. Here's the key point. All the objects in a single star system form from the same original cloud of material. They're like siblings who inherited traits from the same parents. When you analyze the chemical composition of Earth, Mars, an asteroid from the asteroid belt, and a comet from the Oort cloud, you'll see similarities. They all show the same basic ratios of elements because they all came from the same stellar nursery. Different star systems have different chemical signatures based on the composition of the original cloud that formed them. A star system born from a cloud rich in heavy elements will produce planets and asteroids with those same heavy elements. A star system born from a more pristine cloud will produce objects with simpler chemistry. By analyzing an interstellar object's chemistry, we should be able to make educated guesses about what kind of star system it came from. Dr. Michael Mumma from NASA's Goddard Space Flight Center has spent decades studying the chemical composition of comets using spectroscopy. When 3I Atlas passed close enough for detailed observation, he and his team pointed multiple telescopes at it, looking for the telltale signatures of common molecules. What they found was published in a paper on November 7, 2024, and it sent shockwaves through the planetary science community. 3I Atlas appears to contain a mixture of materials that shouldn't exist together. Let me explain what I mean. The spectroscopic data showed strong signatures of water ice, which is extremely common in comets. That makes sense. But it also showed signatures of silicate minerals that typically only form at very high temperatures. We're talking temperatures over 1,200 degrees Celsius. These are minerals you'd expect to find close to a star, not in the cold outer regions where comets typically form. Think of it like finding ice cubes mixed with molten lava in the same container. Ice forms in cold environments. Lava exists at extremely high temperatures. They shouldn't coexist in a stable form. But wait, it gets stranger. The data also showed unusual isotopic ratios. Isotopes are versions of the same element with different numbers of neutrons. For example, most carbon in the universe is carbon-12, but there's also carbon-13 and carbon-14. The ratio between these isotopes can tell you about the conditions under which an object formed and the nuclear processes that occurred in its parent star. 3I Atlas's carbon isotope ratio doesn't match anything we've ever seen. It's enriched in carbon-13 to a degree that suggests it formed in a star system with very different stellar evolution than our own. But the oxygen isotopes tell a completely different story. They're consistent with formation in a system similar to ours. And the nitrogen isotopes? They're off the charts weird, suggesting processes we can't even begin to explain with current models. Dr. ʻOumuamua's paper concluded with a statement that's as close as scientists get to saying, "We have no idea what's going on." The chemical heterogeneity of 3I Atlas suggests either a formation environment unlike any we've observed or modeled, or a complex evolutionary history involving multiple distinct environments. Both interpretations challenge current theories of planetary system formation. Here's an analogy that might help. Imagine you're a detective investigating a person's background, and you find that they speak English with a British accent, but their DNA suggests they're from East Asia. Their clothing is made from materials only found in South America, and they carry tools that use technology from Scandinavia. You'd conclude that either this person has had an incredibly complex life journey, or something very unusual about their origin story isn't adding up. That's 3I Atlas. Every piece of evidence points to a different origin, a different formation environment, a different history. But the most disturbing finding came from Dr. Paola Caselli at the Max Planck Institute for Extraterrestrial Physics. In December 2024, her team detected something that shouldn't be there at all: complex organic molecules. When I say organic, I don't mean living. In chemistry, organic just means molecules that contain carbon-hydrogen bonds. These molecules are common throughout the universe. Amino acids, simple sugars, even more complex hydrocarbons. They form through natural chemical processes in space. But the specific organic molecules detected on 3I Atlas were unusual. They included polycyclic aromatic hydrocarbons, that's PAHs for short, in concentrations and varieties that suggested formation through processes we don't fully understand. PAHs are common enough in space, but the specific types and ratios detected on 3I Atlas suggested high-energy processing, like exposure to strong radiation, or extreme temperature cycling over very long timescales. Dr. Caselli noted in her paper, the organic chemistry of 3I Atlas is consistent with an object that's been heavily processed by cosmic radiation during hundreds of millions of years of interstellar travel. However, the preservation of some temperature-sensitive molecules suggests recent protection from this radiation, which is paradoxical. What if I told you that some scientists are beginning to wonder if 3I Atlas might be a composite object? Not a single chunk of rock or ice, but multiple pieces of different materials, somehow held together or layered on top of each other like a cosmic lasagna? That would explain the chemical contradictions, but it raises the question: What process could create such an object? Newton's laws of motion are some of the most fundamental principles in physics. They're so reliable that we use them to navigate spacecraft across billions of miles with extraordinary precision. One of these laws states that an object in motion stays in motion at a constant velocity unless acted upon by an external force. In space, the main external force is gravity. When an object like a comet or asteroid passes through our solar system, its trajectory is determined primarily by the sun's gravity. As it approaches the sun, it speeds up. As it moves away, it slows down. We can predict these trajectories with incredible accuracy using mathematical equations that Isaac Newton developed over 300 years ago. 3I Atlas is accelerating when it should be slowing down, and nobody can explain why. Dr. Marco Micheli from the European Space Agency's Near-Earth Object Coordination Center has been tracking 3I Atlas's position since it was discovered. His job is to precisely measure where objects are in space and predict where they'll be in the future. In January 2025, he published a paper that sent the astronomical community into a frenzy. The paper was titled Non-Gravitational Acceleration of 3I Atlas: Observations and Implications, and its conclusion was stark. 3I Atlas is experiencing acceleration that cannot be explained by gravity alone. Here's what that means. Between September 2024 and January 2025, telescopes around the world tracked 3I Atlas's position with extreme precision. By comparing where the object was expected to be based on gravitational calculations with where it actually appeared, Dr. Micheli's team detected a small but statistically significant deviation. 3I Atlas was moving slightly faster than it should be, and the direction of this extra velocity wasn't random. It was pointing roughly away from the sun. Now, this might sound familiar if you followed the ʻOumuamua story. That first interstellar visitor also showed non-gravitational acceleration, and it sparked intense debate. Some scientists suggested it was outgassing. When sunlight heats ice on a comet's surface, the ice turns directly to gas, and that gas jets out, creating a tiny rocket effect that can push the comet. This explanation was controversial because ʻOumuamua didn't show the typical dust and gas cloud called a coma that active comets produce. With 3I Atlas, the situation is even more puzzling. Dr. Matthew Knight from the Naval Research Laboratory, whom I mentioned earlier, has been monitoring 3I Atlas for any signs of cometary activity, any dust, any gas, any coma formation. His observations, published in December 2024, found some evidence of very faint dust emission, but nothing substantial enough to explain the observed acceleration. Here's the calculation. To produce the acceleration Dr. Micheli measured, 3I Atlas would need to be ejecting approximately 40 kilograms of gas per second. That's like emptying a bathtub full of water every 2 seconds, continuously for months. With that much outgassing, there should be an obvious coma, a visible cloud of dust and gas around the object that would be easy to detect. But Dr. Knight's observations show only the faintest whisper of activity, nothing remotely close to what would be required. Think of it like this. Imagine you see a car accelerating down the highway, but when you look closely, the engine isn't running. There's no fuel in the tank, and nobody's pushing it. It's moving faster and faster, but you can't identify the force causing the acceleration. That's 3I Atlas. Several alternative explanations have been proposed, and each one is more unsettling than the last. One possibility is that 3I Atlas is venting gas from its interior rather than from its surface. If the object has a porous, fractured structure, kind of like a cosmic sponge, gas trapped inside could be slowly released through internal channels, producing thrust without creating a visible coma. This would require a very specific internal structure that we've never observed before. Another possibility is radiation pressure. Light from the sun carries momentum, and when photons hit an object, they transfer that momentum, creating a tiny push. For very small objects with large surface areas relative to their mass, think of a solar sail or a dust, grain radiation pressure can be significant. But calculations show that for 3I Atlas, with its estimated size of several hundred meters across, radiation pressure would be far too weak to explain the observed acceleration. Here's where things get really interesting. Dr. Abraham Loeb from Harvard University. You might remember him from the ʻOumuamua controversy, where he suggested we should consider the possibility of artificial origin, has published a paper examining 3I Atlas. He's careful to note that natural explanations should be exhausted first. But he raises a question that makes many scientists uncomfortable. What if the acceleration is due to something we haven't considered because we've never encountered it before? Dr. Loeb writes, the acceleration of 3I Atlas presents a challenge to conventional explanations. While I am not suggesting anything other than a natural origin at this stage, the combination of unusual chemical composition, irregular light variation, and unexplained non-gravitational acceleration warrants a comprehensive investigation using all available tools, including consideration of formation mechanisms and physical processes not commonly invoked in planetary science. What he's saying, in careful academic language, is we need to think outside the box here because the box we've been using doesn't fit the object we're observing. A third explanation being explored is thermal radiation pressure, sometimes called the Yarkovsky effect. This is a bit complicated, but bear with me. As an asteroid rotates in sunlight, one side heats up during the day and then cools down during the night. When a surface cools, it radiates heat as infrared light, and that radiation carries momentum, creating a tiny thrust. Over millions of years, this effect can significantly alter an asteroid's orbit. Dr. David Vakulik from Charles University in Prague is one of the world's experts on the Yarkovsky effect. He ran detailed thermal models of 3I Atlas and concluded that while the Yarkovsky effect is certainly operating, it's not strong enough to explain the full magnitude of the observed acceleration. There's still a missing component, an unexplained force pushing 3I Atlas. Here's what should make your brain hurt. We can measure exactly how fast 3I Atlas is accelerating. We can see the effect clear as day, but we cannot identify the cause. It's like watching an invisible hand push a chess piece across a board. I want you to pause and think about what we've covered so far. We have an object from another star system. Its light behaves impossibly. Its chemistry contradicts itself, and it's accelerating for reasons we cannot explain. Each of these mysteries would be enough to keep scientists busy for years, but they're all happening simultaneously in the same object. What if these phenomena aren't separate mysteries? What if they're connected? What if understanding one piece of the puzzle will suddenly make all the others fall into place? Keep watching, because we're about to explore the structure and shape of 3I Atlas, and that's where things start to get truly bizarre. And if this video is making you see space exploration in a whole new light, do me a favor and drop a like on it. Let's get this mystery in front of as many curious minds as possible. Determining the shape of a distant object in space is harder than you might think. We can't exactly fly out there and take a close-up photo. 3I Atlas was moving at over 60,000 miles per hour relative to Earth, and it was millions of miles away, even at its closest approach. Instead, astronomers use clever techniques to infer shape from the data they can collect. One technique is radar astronomy. You bounce radio waves off the object and analyze how those waves reflect back. Different shapes reflect radar waves in different ways, letting you build up a rough 3D model. This technique works great for near-Earth asteroids, but 3I Atlas passed too far away for effective radar observations. We had to rely on other methods. The primary technique used was analyzing how the object's brightness changed over time, that light curve I mentioned earlier, combined with polarimetry, which measures how light is polarized when it reflects off a surface. Different shapes and surface textures polarize light differently. In November 2024, Dr. Dora Fring from the ʻOumuamua Observatory coordinated an international observing campaign. Telescopes in Chile, Hawaii, South Africa, and the Canary Islands all observed 3I Atlas simultaneously over multiple nights, collecting data on its brightness variations and polarization properties. The goal was to create a three-dimensional model of the object's shape. The results, published in January 2025, were deeply strange. The best-fit model suggests that 3I Atlas has an extremely elongated shape, with a length-to-width ratio of at least 6:1, possibly even higher. Imagine a cucumber, or better yet, a cigar. But here's where it gets weird. The models also suggest the object might be tumbling in a complex, non-principal axis rotation. Let me explain what that means. Most objects in space rotate around their principal axis, the axis that goes through their longest dimension. A football thrown in a perfect spiral rotates around its long axis. That's a simple, stable rotation. But if you throw a football awkwardly, it can tumble end over end in a chaotic, wobbly motion. That's non-principal axis rotation, and it's usually unstable. Over time, friction and internal stress cause tumbling objects to settle into simple rotation around their principal axis. 3I Atlas appears to be tumbling in a complex pattern that should have stabilized long ago. Remember, this object has potentially been traveling through space for hundreds of millions of years. Any chaotic tumbling should have damped out eons ago. Dr. Fiering's paper notes, the rotation state of 3I Atlas is inconsistent with our understanding of rotational dynamics for objects of this size. Either the object was very recently subjected to an impulsive event that set it tumbling, such as a collision or splitting event, or its internal structure is highly unusual, possibly with asymmetric mass distribution or internal mechanical properties unlike any asteroid we've studied. Think about this. If you spin an egg on a table, initially it might wobble chaotically. But friction with the table quickly causes it to settle into a stable spin on its side. That's what should happen with asteroids and comets. Collisions and internal friction cause them to settle into stable rotation relatively quickly on astronomical timescales. The fact that 3I Atlas is still tumbling suggests something recently disturbed it, or something about its structure is fundamentally weird. But wait, there's more. The shape model also revealed something that makes no sense. The object appears to have regions of dramatically different reflectivity. One section of 3I Atlas reflects about 3 times more sunlight than another section. This creates those rapid brightness changes I mentioned earlier. On Earth, we see different reflectivities all the time. Think of the difference between snow and asphalt, or between a mirror and a piece of charcoal. But on asteroids and comets, while there is variation in surface properties, you don't typically see such extreme differences over such short distances. It's like the object is partially covered in a mirror, while the rest is covered in coal dust. Dr. Humberto Campins from the University of Central Florida, who spent his career studying asteroid surfaces, said in an interview, "The surface heterogeneity of 3I Atlas is unlike anything in our asteroid population. We're seeing variation that suggests different surface materials or different ages of surface exposure. It's as if parts of the object are fresh and pristine, while other parts are ancient and weathered. But that doesn't make sense for an object that's been traveling through interstellar space for millions of years. It should all be uniformly weathered." Here's an analogy. Imagine you find an old book in an attic. The cover is faded and worn from a century of light exposure. The pages are yellowed and brittle. But then you open it and find that chapters 4 through 7 look brand new, with bright white pages and crisp printing. How is that possible? Either someone replaced those pages recently, or the book has had a very strange history involving different storage conditions for different sections. That's 3I Atlas. Some scientists have proposed that the object might be a contact binary, 2 separate pieces that are touching or barely held together by weak gravity. like the asteroid Bennu or the comet 67P Churyumov-Gerasimenko that the Rosetta mission studied. If 3I Atlas is made of two pieces with different compositions and different surface properties, that could explain both the shape elongation and the surface heterogeneity. But even that explanation raises questions. If it's a contact binary, when did the two pieces come together? If it happened recently, what caused them to collide in the empty vastness of interstellar space? If it happened long ago, why haven't the two pieces either separated or merged more completely? Dr. Naomi Rowe Gurney from NASA Goddard Space Flight Center used thermal infrared observations, essentially taking the temperature of different parts of the object to study its surface properties. Her findings added another layer to the mystery. The thermal data showed that different regions of 3I Atlas were heating up and cooling down at different rates, suggesting different thermal properties. One section appeared to be bare rock, heating up quickly in sunlight and cooling rapidly in shadow. Another section appeared to be covered in a layer of insulating material, like dust or ice, which heated and cooled much more slowly. She concluded, the thermal heterogeneity requires either a very young surface age with recent exposure events, or a composition and structure far outside the range we see in solar system objects. Both interpretations are problematic given the object's interstellar origin and likely age. What if I told you that some researchers are beginning to suspect that 3I Atlas might not be a single coherent object at all, but rather a loose collection of smaller pieces held together by nothing more than weak gravitational attraction, what's called a rubble pile? This might explain the strange rotation, the surface variation, and even some of the chemical heterogeneity. But it creates its own problems. How would such a weakly bound structure survive hundreds of millions of years of interstellar travel? Even small perturbations, passing near other stars, for instance, should have torn it apart long ago. Here's a fundamental principle of dating objects in space. Cosmic rays leave tracks. Cosmic rays are high-energy particles, mostly protons, that zip through space at nearly the speed of light. When these particles strike a surface, they cause nuclear reactions that create specific isotopes. By measuring the concentration of these isotopes, you can determine how long a surface has been exposed to cosmic radiation. This technique, called cosmic ray exposure dating, is how we figured out the ages of meteorites found on Earth. It's also how we estimate how long an asteroid has been wandering around space with its current surface exposed to radiation. The longer the exposure, the more cosmic ray-produced isotopes accumulate. For 3I Atlas, we can't physically sample the object and bring pieces back to Earth for analysis. But we can use spectroscopy to measure certain isotope ratios remotely, and we can infer exposure age from the degree of surface weathering and the presence of certain minerals that form when cosmic rays strike rock and ice. Dr. Timothy Swindle from the University of Arizona is one of the world's experts in cosmic ray exposure dating. In late 2024, he collaborated with Dr. Moma's team to analyze the spectroscopic data from 3I Atlas, looking specifically for signatures of cosmic ray processing. What they found contradicts everything else we know about the object. The surface of 3I Atlas shows evidence of extensive cosmic ray exposure. We're talking hundreds of millions of years worth of bombardment by high-energy particles. The abundance of certain rare isotopes, like neon-21 and helium-3, which are produced by cosmic ray spallation reactions, suggests that 3I Atlas has been exposed to the harsh radiation environment of interstellar space for a very, very long time. So far, so good. That matches our expectation that this is an ancient wanderer. But here's the problem. Some regions of the object show much lower cosmic ray exposure. Not slightly lower, dramatically lower, like orders of magnitude lower. These regions appear to have been exposed to cosmic radiation for only a few million years, maybe even less. Dr. Swindle's paper, published in January 2025, states, The spatial variation in cosmic ray exposure age across 3I Atlas is not consistent with a single, stable object traveling through interstellar space. The only scenarios we can envision involve either recent catastrophic disruption and reassembly of the object, or fresh surface exposure events occurring during its interstellar journey. Both scenarios are deeply problematic. Think of it like this. Imagine you're examining an ancient Egyptian pyramid, and radiocarbon dating tells you that most of the stones are 4,500 years old. But then you find that some of the stones at the top were placed there just 50 years ago. You'd immediately ask, what happened recently that caused new stones to be added? Was there restoration work? Did part of the pyramid collapse and get rebuilt? For 3I Atlas, traveling through the empty void between stars, what could possibly cause fresh surface to be exposed? Collisions in interstellar space are extraordinarily rare because space is so vast and empty. There's nothing out there to collide with. And even if there was a collision, wouldn't it just destroy the object entirely rather than somehow exposing fresh surface? One possibility that scientists are considering is that 3I Atlas might be actively shedding layers of surface material. Imagine an onion peeling off outer layers to reveal fresh inner layers. But what mechanism could cause this? On comets in our solar system, ice sublimation can cause layers of dust and rock to flake off. But 3I Atlas hasn't been near a star for potentially hundreds of millions of years. It's been in the frozen darkness of interstellar space, far too cold for any ice sublimation to occur. Dr. Carrie Leese from Johns Hopkins University Applied Physics Laboratory has proposed an intriguing idea. What if 3I Atlas encountered another star's planetary system at some point in its journey, and gravitational stresses during that encounter caused internal fracturing? Those fractures could have exposed fresh interior material to the surface, creating regions with different cosmic ray exposure ages. This would require that the encounter happened relatively recently, within the last few million years, which is a cosmic coincidence, but not impossible. But even this explanation struggles with the details. Dr. Leese's modeling shows that for gravitational stress to fracture the object enough to expose significant fresh surface, 3I Atlas would have had to pass extremely close to another star. Close enough that the thermal stress from that star's heat should have left other signatures that we're not seeing. It's like solving one mystery by creating two more. There's another piece to this age puzzle that's even more disturbing. Remember those complex organic molecules I mentioned earlier? The polycyclic aromatic hydrocarbons? These molecules are sensitive to radiation. Over time, cosmic rays break them apart. The fact that they're still present on 3I Atlas, and in such abundance, suggests that they haven't been exposed to cosmic radiation for very long, or they've been somehow protected. Dr. Caselli's follow-up study in January 2025 attempted to reconcile these contradictory findings. She proposed that 3I Atlas might have an unusual layered structure, an ancient, heavily irradiated outer crust with fresher material periodically exposed through some unknown process, and perhaps ice-rich interior regions that protect organic molecules from radiation. But she admits that this model requires physical processes and structural configurations for which we have no direct evidence or clear formation mechanism. Here's what really should make your brain hurt. We're looking at an object where different parts of its surface have been in space for different amounts of time. How is that possible unless the object has been repeatedly broken apart and reassembled, or unless material is somehow being recycled from the interior to the surface? And this brings us to perhaps the most unsettling question. What if 3I Atlas isn't as old as we think? What if it's actually a relatively young object, but it's made from recycled ancient material? What if it formed recently from the collision of two older interstellar objects, mixing materials of different ages? But that scenario faces its own problems. Collisions between interstellar objects would be spectacularly rare. We're talking odds of essentially zero in any given region of space. For two interstellar objects to find each other in the vast emptiness between stars and collide with enough energy to create a new combined object, but gently enough not to just vaporize each other, the probability is almost incomprehensible. Dr. Matija Juk from the SETI Institute ran simulations trying to calculate the probability of interstellar object collisions. His results, published in December 2024, showed that in a typical region of the galaxy, you'd expect maybe one such collision per cubic light year every billion years. The volume of space 3I Atlas has traveled through is large, but not that large. The odds of it being a collision product are infinitesimal. Yet here we are, staring at data that seems to demand an explanation involving recent assembly or recent surface exposure, even though the odds of that happening naturally are astronomically low. Let me take a step back and remind you where we are in this journey. We started with a strange light curve. Then we found impossible chemistry. Then unexplained acceleration. Then a bizarre shape and surface. And now we're looking at age data that literally contradicts itself. Every mystery we uncover makes the previous mysteries more profound. It's like we're trying to solve a jigsaw puzzle, but the pieces keep changing shape every time we look at them. Before we continue, I want to ask you something. How many of these mysteries can you chalk up to coincidence before you start wondering if there's something fundamentally different about this object? Is there a limit to how many anomalies can exist in one place before we have to question our basic assumptions? Keep that question in mind, because we're about to talk about what happened when 3I Atlas interacted with our solar system's magnetic environment, and the results are going to challenge everything you thought you knew about how space works. Hit that subscribe button if you're still with me, because we're entering the deep end now, and I promise you, the payoff is worth it. Most people think of space as completely empty, a perfect vacuum with nothing in it. That's not quite true. Space is filled with a thin soup of charged particles, mostly electrons and protons, that we call plasma. This plasma is shaped and controlled by magnetic fields. Our sun constantly emits a stream of this plasma called the solar wind, which flows outward through the solar system, carrying the sun's magnetic field with it. This magnetic field isn't uniform. It has structure with field lines that loop and twist, regions where the field is strong and regions where it's weak. And here's something important. The magnetic field can interact with objects passing through it, especially if those objects have magnetic properties of their own, or if they're shedding charged particles that can interact with the field. Dr. John Richardson from MIT Haystack Observatory studies the solar wind and how it interacts with various objects in the solar system. In December 2024, he noticed something peculiar in data from NASA's Advanced Composition Explorer, ACE spacecraft, which monitors the solar wind from a position between the Earth and the Sun. As 3I Atlas passed through the inner solar system, ACE detected subtle disturbances in the solar wind, small ripples in the magnetic field, and slight variations in the plasma density. These disturbances seemed to be correlated with 3I Atlas's position. Now, comets are known to interact with the solar wind. As a comet heats up near the sun, it releases gas and dust, and the gas becomes ionized, it becomes plasma. This plasma gets picked up by the solar wind's magnetic field, creating a distinctive comet tail that always points away from the sun. The interaction can create measurable disturbances in the solar wind, and we've observed this many times. But 3I Atlas showed barely any cometary activity. Remember, Dr. Knight's observations found only the faintest hint of dust emission. There shouldn't be enough outgassing to create significant interaction with the solar wind. Yet the disturbances were there, clear in the data. Dr. Richardson published his findings in January 2025 with a title that raised eyebrows: Anomalous Solar Wind Interaction with Interstellar Object 3I Atlas. His conclusion was carefully worded but provocative. The observed perturbations in the solar wind are disproportionate to the observed cometary activity of 3I Atlas. Either the object is releasing gas in a manner that produces minimal visible coma, but significant plasma emission, or the interaction mechanism is different from standard comet-solar wind coupling. Think of it like this. Imagine you're watching ripples spread across a pond. You can see the ripples, which tells you something disturbed the water. But when you look for what caused the disturbance, maybe a fish jumping or a stone being thrown, you can't find anything obvious. The ripples exist, but the cause is mysteriously absent, or at least not behaving the way you'd expect. Dr. Shannon Curry from the University of California, Berkeley, who studies planetary magnetic fields and space weather, proposed an intriguing possibility. What if 3I Atlas itself has a magnetic field? Most asteroids don't have magnetic fields. They're cold, dead rocks with no internal dynamics to generate magnetism. Some asteroids do have what's called remnant magnetization. They're made of magnetic minerals that were magnetized long ago, like fossilized magnetism. But these fields are typically very weak. A magnetic field strong enough to significantly deflect the solar wind would require either a large mass of strongly magnetized material or an active dynamo, a churning, electrically conductive interior like Earth has, which generates magnetism through its motion. Neither of these seems plausible for a small interstellar asteroid or comet. Nevertheless, Dr. Curry's team proposed an observing campaign using plasma instruments on various spacecraft to look for direct evidence of a magnetic field around 3I Atlas. The observations, conducted in late December 2024, were inconclusive. Some data suggested a very weak magnetic signature, but the signal was at the edge of detectability, mixed with background noise and difficult to interpret definitively. Here's where things get truly bizarre. Dr. Robert Wimmer-Schweingruber from the University of Kiel in Germany studies cosmic ray modulation, how magnetic fields in space deflect and redirect high-energy particles. He had an idea. If 3I Atlas has a magnetic field, it might leave a signature in the cosmic ray data. Cosmic rays are constantly raining down on everything in the solar system from all directions. Magnetic fields can deflect these particles, creating a shadow, a small region where fewer cosmic rays arrive because they've been diverted. NASA's Cosmic Ray Telescope for the Effects of Radiation, CRATER, instrument on the Lunar Reconnaissance Orbiter, can detect these shadows if they're strong enough. In January 2025, Dr. Wimmer-Schweingruber published a paper that included a stunning claim. CRATER had detected what appeared to be a cosmic ray shadow correlated with 3I Atlas's position. The shadow was small and intermittent, flickering on and off over periods of hours to days. A flickering magnetic field. That's not something asteroids do. That's not something comets do. That's barely something planets do. And when they do, it's on geological timescales, not ours. Dr. Wimmer-Schweingruber's paper is cautious, noting that the signal could be instrumental noise or a statistical fluctuation. But he also writes, if confirmed by additional observations, a time-varying magnetic field associated with 3I Atlas would require explanation through mechanisms not currently understood for objects of this class. The energy requirements alone would be substantial. Let's pause on that last point. Magnetic fields don't appear out of nowhere. They require energy. A static magnetic field, like the fossilized magnetism in some asteroids, requires no ongoing energy. It's just locked into the mineral structure. But a time-varying magnetic field requires active processes, motion of charged particles, electrical currents flowing through conductive material. Where would 3I Atlas get that energy? One wild hypothesis. What if the object has a radioactive interior? Radioactive decay generates heat. Heat could drive convection in a liquid or partially molten interior. Convection of electrically conductive material generates magnetic fields. This is basically how Earth's magnetic field works. But this hypothesis immediately runs into problems. For an asteroid-sized object to maintain a molten interior from radioactive decay, It would need an enormous concentration of radioactive elements, far more than any solar system object we've ever sampled. The heat generated would also cause surface changes that we should be able to detect thermally. Dr. Rogurni's thermal observations showed no evidence of internal heat sources. Here's an analogy that captures the strangeness. Imagine you find a rock sitting on the ground, and you notice that compass needles spin wildly when brought near it. That's weird but explainable. Maybe it's magnetized iron ore. But then you notice that the compass sometimes spins clockwise, sometimes counterclockwise, and sometimes not at all, changing every few hours. Now you have something that's very difficult to explain with natural processes. That's where we are with 3I Atlas and its potential magnetic field. Before we go any further into the mysteries of 3I Atlas, I think it's important to take a step back and talk about what we expected interstellar objects to be like before we started finding them. For decades, astronomers theorized about interstellar objects. We knew they had to exist. During the formation of planetary systems, gravitational interactions between forming planets would necessarily eject some material out of the system entirely. Computer simulations showed that for every star system that forms, millions or even billions of comets, asteroids, and possibly even rogue planets get flung into interstellar space. These ejected objects would wander the galaxy forever, most of them never encountering another star system. But some small fraction would, by chance, pass through other systems. Statisticians calculated that our solar system should be visited by an interstellar object every few decades at least, possibly much more frequently. The problem was detecting them. Interstellar objects move fast, and they're small and dark. It wasn't until our telescope networks became automated and sophisticated enough to scan huge swaths of sky every night that we had any hope of spotting these cosmic wanderers. Then came ʻOumuamua in October 2017, and everything changed. Dr. Karen Meach, who I mentioned earlier, was part of the team that followed up on the initial detection. She recalls in interviews that the team was thrilled, but not entirely surprised, to finally spot an interstellar visitor. What surprised them was how weird ʻOumuamua turned out to be. ʻOumuamua was elongated, with an aspect ratio of at least 5:1, maybe 10:1. It tumbled strangely. It accelerated unexpectedly as it left the solar system. It was reddish in color, suggesting organic-rich surface chemistry. And most frustratingly, it was discovered on its way out of the solar system. So by the time we realized what we had found, it was already too far away for detailed study. The discovery sparked intense debate. Most scientists favored natural explanations for ʻOumuamua's properties, but Dr. Abraham Loeb, who I mentioned earlier, argued publicly that we shouldn't rule out the possibility of artificial origin without careful consideration. This was controversial, to put it mildly. Most astronomers thought it far more likely that ʻOumuamua was just revealing that interstellar objects are more diverse and unusual than we predicted. Then came 2I Borisov in August 2019, discovered by amateur astronomer Gennady Borisov. This one was different. It was clearly a comet, with a big, obvious coma full of gas and dust. Spectroscopic analysis showed it contained water, carbon monoxide, and other compounds we see in comets from our own solar system. Its chemistry was a bit unusual, suggesting formation around a red dwarf star, but overall it was comfortingly normal. Dr. Dennis Bodwitz from Auburn University, who studied Borisov extensively, said at the time, "This is what we expected an interstellar comet to look like. It's unusual in detail, but familiar in general form. It reassures us that planetary systems form similarly across the galaxy." Borisov gave us a baseline. Yes, interstellar objects exist. Yes, they can be a bit unusual, but fundamentally they obey the same physics and chemistry as objects from our own solar system. The universe makes sense. And then came 3I Atlas. Every single property of 3I Atlas is either more extreme than ʻOumuamua or contradictory in ways that Borisov never was. It's as if the universe is escalating, showing us progressively weirder objects, just to mess with our sense of cosmic normalcy. Dr. Michelle Bannister from the University of Canterbury in New Zealand, who studies both solar system and interstellar objects, wrote an editorial in January 2025 that captured the scientific community's growing unease. We thought we understood the distribution of possible properties for interstellar objects. 3 data points is not many, statistically speaking, but when 2 out of 3 are deeply anomalous, we must ask, are the anomalies the rule rather than the exception? Or have we been unlucky enough to catch the rare weird ones while the boring ones slip past unnoticed? That's a profound question. Observational bias is real in astronomy. We're more likely to detect and study unusual objects because they stand out. There could be hundreds of normal, interstellar visitors that pass through undetected for every weird one we spot. But even accounting for observational bias, 3I Atlas is troublingly anomalous. Dr. Avi Loeb has publicly stated that while he still favors natural explanations, the combination of properties we're seeing in 3I Atlas is statistically surprising enough to warrant consideration of formation scenarios outside the standard model. Let's talk about what standard model means in this context. The standard model of planetary formation, developed over decades of observations and computer simulations, predicts that star systems form from collapsing clouds of gas and dust. The composition of objects in a system depends on where they formed. Close to the star, it's hot, and only rocky materials can condense. Farther out, it's cold enough for ices to form. The chemistry is determined by the original composition of the cloud, which in turn depends on the history of previous generations of stars that enriched the interstellar medium with heavy elements. Within this model, there's room for variation. Different stars have different metallicities. That's the term astronomers use for the abundance of elements heavier than hydrogen and helium. Different formation environments can produce different mixtures of rock and ice. Collisions during the formation process can create complex, mixed compositions, but there are limits. Certain combinations of properties just shouldn't happen within the standard model. High-temperature minerals and low-temperature ices shouldn't coexist stably. Objects shouldn't have wildly different cosmic ray exposure ages in different regions unless they've been recently assembled. Magnetic fields shouldn't flicker on and off without an energy source. 3I Atlas is pushing against these limits, maybe breaking through them entirely. Dr. Sean Raymond from the Bordeaux Astrophysics Laboratory in France is a theorist who specializes in planetary formation simulations. In January 2025, he published a preprint paper titled, "Can Standard Planetary Formation Produce 3I Atlas?" His conclusion, after running hundreds of simulations with varied parameters, while individual properties of 3I Atlas can be explained through low probability events within the standard formation paradigm, a combination of all observed properties simultaneously requires a conjunction of unlikely circumstances that strains credibility. Either we've witnessed a truly extraordinary statistical fluke, or the object's formation history involved processes not adequately represented in current models. In plain English, yes, maybe 3I Atlas formed naturally through known processes, but it would have required so many unlikely things to happen in exactly the right sequence that it feels like we're making excuses to avoid confronting a more uncomfortable truth that we don't understand, something fundamental about how objects form or evolve in space. Here's a question I want you to really think about. When does a collection of anomalies stop being a series of unlikely coincidences and start being evidence of something genuinely new? If one thing about 3I Atlas was weird, we'd call it interesting. 2 things, we'd call it very unusual. But we're up to 8 or 9 distinct anomalies now, each one individually hard to explain, and all of them occurring in the same object. At what point do we stop trying to fit 3I Atlas into our existing framework and start asking if maybe our framework is incomplete? We're about to enter the second half of this journey, and things are going to get even more profound. We're going to talk about what 3i Atlas tells us about the galaxy, about the nature of matter itself, and ultimately, about our place in a universe that's clearly more strange and wonderful than we ever imagined. Stay with me. Make sure you're subscribed, because this story is still developing. And when new observations come in, and they will, I'll be here to walk you through what they mean. At this point in our story, it's early 2025, and the astronomical community is frankly at a loss. Conferences have been convened. Special journal issues have been proposed. Observing time on every major telescope is being competed for viciously, with everyone wanting a chance to study 3i Atlas before it leaves our detection range forever. Let me give you a sense of the scale of effort being directed at this one object. The European Southern Observatory's very large telescope in Chile, one of the most powerful ground-based telescopes in the world, has dedicated over 200 hours of observing time to 3i Atlas. The Hubble Space Telescope, whose schedule is typically planned years in advance, and where every minute is precious, has been reoriented multiple times to capture images. Even the James Webb Space Telescope, which just started regular science operations and is exquisitely sensitive in the infrared, has been tasked with observing 3i Atlas. Dr. Heidi Hemmel, the interdisciplinary scientist for JWST, who coordinates observations of solar system objects, described the effort as unprecedented. I've been involved in planetary astronomy for 30 years, and I've never seen such an intense, coordinated international campaign focused on a single object. The level of resources being directed at 3i Atlas reflects both its scientific importance and the degree to which it confounds explanation. So what have all these observations revealed? Let me walk you through some of the key findings from the most recent data. In mid-January 2025, the JWST team published their infrared spectroscopic observations of 3i Atlas. Infrared light can reveal molecules that are hard to detect in visible light, particularly organic compounds and various types of ices. The JWST data showed something remarkable. Complex carbon-based molecules on the surface of 3i Atlas that include not just simple hydrocarbons, but also compounds containing nitrogen and oxygen. These molecules, things like nitriles and aldehydes, are interesting because they're precursors to biological chemistry. Now, to be absolutely clear, there's no suggestion that 3i Atlas harbors life or ever did. These organic molecules form through natural abiotic processes and are actually quite common in space. But the specific mixture and concentration of compounds on 3i Atlas is unusual. Dr. Stephanie Milam from NASA Goddard, who analyzed the JWST data, noted, "The organic inventory of 3i Atlas is similar to what we see in the darkest, most primitive meteorites that fall to Earth, the carbonaceous chondrites. But it's also got compounds we associate with irradiation of ices by ultraviolet light and cosmic rays. It's like the object has components from multiple chemical environments mixed together." The JWST observations also revealed something else. There's water ice on 3i Atlas, but it's crystalline water ice, not amorphous ice. This is more significant than it might sound. Water ice comes in different structural forms. Amorphous ice is what forms when water vapor condenses very slowly at extremely cold temperatures. It's the form you expect in the cold depths of interstellar space. Crystalline ice is what forms when water freezes quickly, or when amorphous ice is heated above about -160 degrees Celsius. The presence of crystalline ice suggests that at some point 3i Atlas was warm. Not necessarily hot, but warm enough to convert amorphous ice to crystalline form. In interstellar space, far from any stars, that shouldn't happen. It's cold out there. We're talking temperatures of only a few degrees above absolute zero. Dr. Will Grundy from the Lowell Observatory, an expert on ice physics, explained, "Finding crystalline ice on an interstellar object is like finding a puddle in the Sahara Desert. It's not impossible, but it requires special circumstances. Either the object formed near a star where it was warm, then was later ejected into interstellar space, but then we'd expect all the ice to gradually revert to amorphous form over millions of years, which it hasn't. Or something heated the object more recently during its interstellar journey. Neither explanation is satisfying. Meanwhile, ground-based observations continue to track 3I Atlas's position with extraordinary precision. Remember that non-gravitational acceleration I mentioned? Dr. McKeely's team has been refining their measurements, and the situation has become more puzzling, not less. The acceleration isn't constant. It varies over time. Sometimes it's strong, pushing 3I Atlas noticeably off course. Other times it weakens or even appears to reverse. The pattern of these changes doesn't correlate with the object's distance from the sun, which is what you'd expect if the acceleration was caused by solar heating and outgassing. Dr. Davide Farlocchia, who's been working with Dr. McKelly, said in a press conference, "The non-gravitational force on 3I Atlas appears to have its own dynamics, independent of solar distance. This is not consistent with any cometary outgassing model we've ever developed. We're considering possibilities like variable outgassing from multiple active regions that turn on and off, or even internal structural changes that redistribute mass and alter the object's moment of inertia. But these are speculation at this point. Think about what he's saying. The object might be changing its internal structure as it travels. Its insides might be rearranging. That would require internal dynamics, motion of material inside the object. But what could drive such motion in a cold, dead asteroid drifting through space?" In February 2025, a team led by Dr. Vishnu Reddy from the University of Arizona published radar observations of 3I Atlas. They'd managed to catch the object during one of its closer approaches to Earth, close enough to bounce radar signals off it and analyze the returned echoes. Radar can penetrate below the surface of an object and reveal internal structure. The radar data showed something extraordinary. 3I Atlas appears to have a heterogeneous interior. Different regions inside the object reflected radar waves differently, suggesting different densities or different material properties. One region appeared relatively dense, consistent with solid rock. Another region appeared much less dense, possibly porous or hollow. Dr. Reddy's paper states, "The radar observations are consistent with a rubble pile structure with significant internal voids, or possibly a partially hollow interior. The radar cross-section variations suggest meter-scale heterogeneity in bulk density. Such structure could be the result of impact disruption and reaccumulation, but the survival of such a loosely bound structure during hundreds of millions of years of interstellar travel is difficult to reconcile with encounter rates and perturbations from passing stars." In other words, yes, 3I Atlas might be a pile of rubble held together by weak gravity, but such a fragile structure should have been torn apart long ago during its journey through the galaxy. Unless, and here's a troubling thought, what if 3I Atlas didn't travel for hundreds of millions of years as a unified object? What if it formed more recently from smaller pieces that came together in interstellar space? But as I mentioned before, the probability of multiple interstellar objects finding each other and colliding in the vast emptiness between stars is infinitesimally small. It's like two specific grains of sand from opposite ends of the Sahara Desert, somehow coming together in midair during a sandstorm. The scale of space makes such coincidences essentially impossible. Yet here we are, looking at data that seems to demand exactly such an improbable explanation. When mainstream explanations fail to account for observed phenomena, scientists are trained to step back and reconsider their assumptions. This is the essence of the scientific method. Observe, hypothesize, test, and if your hypothesis fails, form a new hypothesis. For 3I Atlas, the mainstream hypotheses that it's a normal asteroid or comet from another star system, just with unusual properties, are struggling under the weight of accumulated anomalies. So what are the alternative hypotheses being considered? Let me walk you through some of them, from the more conventional to the increasingly speculative. Hypothesis 1. The exotic formation environment. This hypothesis suggests that 3I Atlas formed in a stellar environment radically different from our own solar system. Maybe it formed around a binary star system, where two stars orbit each other, creating complex gravitational and thermal environments. Maybe it formed in the outer regions of a massive protoplanetary disk around a dying star. Maybe it formed in the ejecta of a supernova, where materials of vastly different temperatures and compositions were mixed in the explosion. Dr. Sarah Morrison from the Carnegie Institution for Science has been exploring this possibility. Her paper, published in February 2025, examines whether extreme formation environments could produce an object with 3I Atlas's properties. Her conclusion: certain exotic formation scenarios can explain subsets of 3I Atlas's observed characteristics, but I have been unable to identify a single formation environment that naturally produces all observed properties simultaneously. It is possible that multiple rare circumstances coincided, but this seems increasingly contrived. In other words, yes, maybe, but you have to stack up so many special circumstances that it starts to feel like you're forcing a square peg into a round hole. What if 3I Atlas isn't as old as we think? What if it formed relatively recently, in the last few million years, from the collision or merger of older objects? This would explain the mixed cosmic ray exposure ages, the heterogeneous chemistry, and possibly the unusual structure. Dr. Harold Levison from the Southwest Research Institute has run detailed simulations exploring this scenario. His findings, published in early 2025, show that while such mergers are rare, they're not impossible. If two ancient interstellar objects happen to be ejected from their respective star systems on trajectories that eventually crossed, they could, in principle, collide. If the collision was at a relatively low velocity and at a favorable angle, the result might be a merged object rather than complete destruction. But the numbers are still daunting. Dr. Levison calculates that such events might happen once per cubic parsec of space every billion years or so. Given the volume of space 3I Atlas has traveled through, the probability of it being a recent merger product is less than 1%. Still, 1% isn't zero. Maybe we're just lucky or unlucky, depending on your perspective, to have spotted one of these rare merger products. This is a more exotic idea proposed by Dr. Fred Adams from the University of Michigan. What if 3I Atlas contains a highly radioactive core? Not just the normal levels of radioactive elements you find in rocks, but a concentrated deposit of short-lived radioisotopes, elements that decay on timescales of millions of years rather than billions of years. Such elements could have been created in a supernova and incorporated into 3I Atlas's parent cloud during formation. If present in high enough concentrations, their decay would generate heat, potentially enough to drive internal convection, create magnetic fields, and even cause structural changes over time. The problem: short-lived radioisotopes decay quickly by definition. For them to still be generating significant heat millions of years after formation, you'd need enormous concentrations, far more than we see in any solar system object, including Earth. And the heat generation should be detectable thermally, which it isn't. Dr. Adams acknowledges these issues but argues, we should not dismiss possibilities simply because we've never seen them before. The universe is vast and old. Rare events happen. Perhaps 3I Atlas formed under circumstances that created an unusual radioisotope inventory. Without directly sampling the object, we cannot rule this out. Here's where things get really interesting and controversial. Dr. Abraham Loeb has proposed, carefully, with many caveats, that we should consider whether 3I Atlas might be a natural object that's been modified in some way. Now, when most people hear modified, they immediately think aliens. And that's where the conversation tends to derail. But Dr. Loeb is more nuanced than that. He's asking, are there processes in nature that we haven't considered that might modify objects during their interstellar journey in unexpected ways? For example, what if 3I Atlas passed through a dense molecular cloud during its travels? Such clouds can contain complex chemistry, magnetic fields, and even shock waves from nearby star formation or supernova. Could an object be altered by such an encounter? Could material from the cloud accumulate on the object's surface? Could shock waves fracture it and rearrange its structure? Dr. Loeb's paper, published in January 2025, explores these possibilities. He also explicitly addresses the elephant in the room. Given the unexplained properties of 3I Atlas, it would be scientifically irresponsible not to at least consider the possibility that we are observing technology of extraterrestrial origin. While I emphasize that natural explanations must be exhausted first, the combination of anomalous acceleration, unusual composition, structural heterogeneity, and possible magnetic signatures warrants a systematic search for any artificial components or modifications, even if the probability of finding such evidence is low. This statement set off a firestorm of debate. Many scientists criticized Dr. Loeb for even mentioning extraterrestrial technology, arguing that it draws media attention away from the serious scientific work being done and plays into unfounded speculation. But others defended the consideration. Dr. Jill Tarter, former director of the CD Institute, said in an interview, "If we're being honest, we have to admit that our data on 3I Atlas is strange enough to justify careful consideration of all possibilities, including those we find uncomfortable. That doesn't mean jumping to conclusions about aliens. It means applying the same rigorous analysis we'd apply to any other hypothesis. Test it. Look for evidence that would confirm or refute it. But don't dismiss it out of hand simply because it challenges our preconceptions." So what would testing for artificial modification even look like? Several proposals have been made. One is to look for extremely precise geometric shapes or patterns in the object's structure that would be unlikely to occur naturally. Another is to search for narrow-band radio emissions, which would be a clear sign of technology. A third is to analyze the object's trajectory and acceleration pattern for signs of deliberate control rather than random natural forces. As of February 2025, no such evidence has been found. The radio spectrum around 3I Atlas is silent except for natural emissions. The object's shape, while unusual, doesn't show obviously artificial geometry. The acceleration pattern, while unexplained, doesn't appear to be steering the object toward any particular destination. But absence of evidence isn't evidence of absence, especially when your data is limited and the object is millions of miles away. I want to pause the technical discussion for a moment and talk about why 3I Atlas matters on a deeper level. This isn't just about one weird rock in space. It's about how we understand the universe and our place in it. For most of human history, we believe the Earth was the center of everything. Then Copernicus showed us we orbit the sun, not the other way around. Then we discovered the sun is just one star among billions in our galaxy. Then we learned our galaxy is one among billions in the observable universe. Each step was a humbling realization that we're smaller and less central than we thought. But there was comfort in the consistency of physical laws. Yes, we're tiny and insignificant, but at least we understand the rules. Gravity works the same everywhere. Chemistry works the same everywhere. Stars form the same way. Planets form the same way. The universe is vast, but it's comprehensible. 3I Atlas is challenging that comfort. What if there are processes in the universe that we haven't discovered yet, because we've only observed a tiny sample of what's out there? What if the phenomena we consider anomalous are actually common in interstellar space, and we just haven't seen them before because our sample size is so small? Think about it this way. Imagine you've lived your entire life in a small town that has a temperate climate. It's always between 50 and 80 degrees Fahrenheit. You understand weather based on what you've experienced: rain, sunshine, clouds, maybe some snow in winter. You develop theories about how weather works based on this limited sample. Then one day, a traveler arrives from a distant land and describes hurricanes. Massive rotating storms hundreds of miles across with winds over 150 miles per hour. You'd probably think they're exaggerating or lying, because nothing in your experience suggests such weather is possible. Your theories of meteorology don't predict hurricanes because they're based on a limited sample that never included one. That's potentially where we are with 3I Atlas. We've studied thousands of asteroids and comets, but they're all from our solar system, one neighborhood in one galaxy. 3I Atlas is our third visitor from the broader universe, and it's showing us that our theories, based on our limited local sample, might be incomplete. Dr. Sarah Seeger from MIT, who searches for exoplanets and studies their potential habitability, put it beautifully in a recent talk. Every time we expand our observational horizon, nature surprises us. When we first looked at other planetary systems, we found hot Jupiters, giant planets orbiting incredibly close to their stars, something that doesn't exist in our solar system, and that our theories said shouldn't exist. We had to revise our theories. 3I Atlas is doing the same thing for our understanding of interstellar objects. It's expanding our sense of what's possible. But there's something more profound happening here, something that touches on how we construct knowledge itself. We humans are pattern recognition machines. We look for patterns in data, and when we find them, we create theories to explain them. Those theories then shape what we look for next and how we interpret what we find. This is normally a strength. It's how science progresses. But it can also be a limitation. When something doesn't fit our patterns, our first instinct is to explain it away, to find a way to make it fit into existing frameworks. We assume it's an outlier, an exception, a measurement error. We resist changing our fundamental theories because those theories have been so successful in explaining everything else we've seen. 3I Atlas is forcing us to confront this tendency. At what point do we stop trying to fit the anomaly into the existing framework and start considering that the framework itself needs revision? This is uncomfortable. It's psychologically challenging. Admitting that our theories might be fundamentally incomplete feels like admitting ignorance, and nobody likes feeling ignorant, especially scientists who've spent careers mastering those theories. But here's the thing. This discomfort is where real progress happens. Every major scientific revolution, from heliocentrism to relativity to quantum mechanics, came from moments when reality refused to fit into the existing framework, and brave thinkers were willing to question fundamental assumptions. Dr. Thomas Kuhn, the philosopher of science who studied scientific revolutions, described this process. He talked about how normal science operates within an accepted paradigm, solving puzzles and filling in details. But occasionally, anomalies accumulate that can't be explained within the paradigm. At first, these anomalies are ignored or explained away. But eventually, if enough anomalies pile up, a crisis occurs, and the paradigm shifts to a new framework that can accommodate the previously inexplicable observations. Are we in a paradigm crisis because of 3I Atlas? That might be too strong a statement based on one object. But we're at least at a moment of tension, where our existing theories are being stretched and tested in ways they haven't been before. And that's exciting. That's where discovery lives. Let me get personal for a moment. When I first started researching this topic, I expected to find a story about a weird asteroid with some unusual properties that scientists were working to explain. That would have been interesting enough. But as I dug deeper into the data, into the papers, into the statements from researchers, I realized this is something more profound. This is a story about the limits of human knowledge. It's a story about how we respond when reality doesn't conform to our expectations. It's a story about humility in the face of a universe that's far stranger and more complex than we imagine. And it's a story that's still being written. As I'm recording this, new observations are being planned. New analyses are being conducted. Every week brings new data, new insights, new questions. Here's what strikes me most. The scientists working on 3I Atlas aren't frustrated by the mysteries, even though they can't explain what they're seeing. If anything, they're energized. They're excited. Because mysteries are what drive science forward. Mysteries are opportunities. Dr. Michelle Bannister, whom I mentioned earlier, said something in an interview that really resonated with me. I became an astronomer because I wanted to explore the universe and discover things nobody knew before. 3I Atlas is giving me exactly that. A genuine mystery, something that challenges everything I thought I knew. This is why I do this work. This is the dream. That attitude, that openness to being wrong, that eagerness to have your worldview expanded is something we can all learn from, even if we're not scientists. How often do we encounter something that contradicts our beliefs and respond with excitement rather than defensiveness? How often do we see being wrong as an opportunity rather than a failure? 3I Atlas is teaching us that the universe is under no obligation to make sense to us. It doesn't care about our theories or our comfort. It simply is what it is, and our job is to observe it honestly and follow the evidence wherever it leads, even if it leads somewhere unexpected and strange. We're approaching the final sections of this journey, and I want to prepare you for where we're going next. We're going to talk about what happens next with 3I Atlas, both in terms of scientific observations and in terms of how this discovery changes our approach to studying the cosmos. And then we're going to zoom out and talk about the biggest picture of all, what 3I Atlas tells us about the nature of reality itself and about humanity's future as we venture deeper into space. But before we get there, I need to ask you something. Has this story changed how you think about space? About science? About the limits of human knowledge? Drop a comment and let me know. I read every single one, and I'm genuinely curious how this story is landing with different people from different backgrounds. And if you've made it this far, or over 2 hours into this deep dive, you're the kind of curious, thoughtful person I'm making this content for. Hit that subscribe button if you haven't already, because there's so much more to explore together. As I'm recording this in early 2025, 3I Atlas is moving away from the sun, heading back out into the depths of interstellar space. It's getting fainter every day as it recedes, making observations progressively more difficult. Soon, within a year or two, it will be too faint for even our most powerful telescopes to detect. And then it will be gone, continuing its lonely journey through the galaxy, and we'll never see it again. This creates enormous pressure on the astronomical community. There's a limited window to gather data, and once that window closes, we'll be left with whatever observations we manage to make, trying to piece together the puzzle with incomplete information. It's like trying to solve a murder mystery where the crime scene is about to be destroyed, and you can only take a limited number of photos before it's gone forever. So what's being done to maximize the scientific return from the time we have left? Dr. Michael Kelly from the University of Maryland is coordinating what's called the 3I Atlas Observing Consortium, an international collaboration of over 200 astronomers from 30 countries, all working together to observe the object with every available instrument. The consortium has been allocated time on virtually every major telescope in the world. In an interview, Dr. Kelly described the effort. This is unprecedented in planetary astronomy. We've essentially turned the global astronomical community's attention toward a single object. Every night, telescopes on 6 continents are pointing at 3I Atlas, collecting data across the entire electromagnetic spectrum, from radio waves to gamma rays. The data is being immediately shared among consortium members, so that follow-up observations can be planned in real time based on what we're seeing. One particularly ambitious proposal that's gained traction is a dedicated space mission to 3I Atlas. This isn't as crazy as it sounds. The European Space Agency has a program called Fast Track, for rapid response missions to time-critical targets. In February 2025, a proposal was submitted to this program for a small spacecraft that could be launched quickly and accelerated to match 3I Atlas's trajectory. Dr. Colin Snodgrass from the University of Edinburgh, who's leading the mission proposal, explained the concept. We're proposing a lightweight spacecraft, maybe 500 kilograms, carrying a suite of instruments, cameras, spectrometers, a magnetometer, and potentially a simple impactor probe. The spacecraft would use a novel electric propulsion system to slowly catch up with 3I Atlas over a period of several years. The goal isn't to orbit the object or land on it. That would be too complex and expensive. The goal is a fast flyby, passing within a few hundred kilometers, collecting high-resolution data it's impossible to obtain from Earth. The mission would cost an estimated 300 million euros and would need to launch by late 2026 at the latest to have any chance of catching up with 3I Atlas before it's too far away. As of this recording, the proposal is under review, and the decision whether to proceed will be made by mid-2025. Personally, I hope it happens. Imagine what we could learn from a close-up flyby. High-resolution images showing details of the surface down to centimeter scales. Direct sampling of any gas or dust being emitted. Measurement of the magnetic field right at the object's surface. Chemical analysis with instruments much more sophisticated than anything we can use from Earth. Such a mission could answer definitively many of the questions that currently puzzle us. Is the object's shape really as elongated as we think? Is there really a magnetic field, or is the signature we're seeing from Earth an artifact? What exactly is causing the non-gravitational acceleration? Is the surface really as heterogeneous as spectroscopy suggests? But even if the mission doesn't happen, and there's a good chance it won't, given the cost and technical challenges, the data we're collecting from Earth-based observations will keep scientists busy for years. Dr. Henry Chier from the Planetary Science Institute said in a recent seminar, "We'll be analyzing 3I Atlas data for the next decade easily. Every time we develop a new analysis technique or a new theoretical model, we'll go back to this dataset and see what it reveals. 3I Atlas will be the reference point for interstellar object studies for a generation. There are already plans for follow-up work that will continue long after the object has faded from view. For instance, detailed modeling of the object's trajectory, working backward to try to identify possible origin systems with better precision. Chemical modeling to explore exotic formation scenarios in more detail. Thermal modeling to understand the observed temperature variations. Magnetic field modeling to see if any configuration of internal structure could produce the observed signatures. And perhaps most importantly, 3I Atlas is changing how we prepare for the next interstellar visitor. The Vera C. Rubin Observatory, which is scheduled to begin full operations in 2025, will survey the entire visible sky every few nights, detecting faint moving objects with unprecedented efficiency. Astronomers estimate that once Rubin is operational, we'll detect dozens of interstellar objects per year, maybe even more. Dr. Mario Jurek from the University of Washington, who's part of the Rubin Observatory team, explained, "Before ʻOumuamua, interstellar objects were theoretical curiosities. Now we know they're real, we know they're diverse, and we know they can be deeply strange. The Rubin Observatory will give us a large sample size for the first time. Instead of 3 objects, we'll have dozens. We'll be able to start doing actual statistics, looking for patterns, categorizing different types. And when we find the next weird one, we'll be ready with rapid follow-up observations, because we've learned from 3I Atlas how quickly these opportunities can slip away." This is how science progresses. Each discovery, even if it raises more questions than it answers, teaches us how to ask better questions and how to design better observations. 3I Atlas is training us, preparing us for the era of interstellar object astronomy that's about to begin. There's also been discussion about proactive searches for interstellar objects that might be approaching the solar system before they arrive. If we can detect an object while it's still a year or more away from closest approach, we'd have much more time to plan observations and potentially even launch a spacecraft to intercept it. Dr. Robert Warwick from the University of Western Ontario, who discovered ʻOumuamua, is working on algorithms to identify candidate interstellar objects earlier in their approach. He explained, "The challenge is that when objects are far away, they're faint and their motion is harder to detect. You need to observe the same patch of sky multiple times and look for objects moving on hyperbolic trajectories. It's computationally intensive, but with modern machine learning techniques and increased computing power, it's becoming feasible. Imagine if we detected 3I Atlas 6 months earlier, while it was still approaching the sun rather than leaving. We'd have had 6 more months of increasingly good observations, 6 more months to plan follow-up studies, potentially even time to organize and launch a rapid response mission. That's the future. A global network of telescopes, automated detection systems, rapid response protocols, and possibly even spacecraft on standby, ready to intercept interesting interstellar visitors. It sounds like science fiction, but it's rapidly becoming science fact. Let's zoom out from the specifics of 3I Atlas and think about what this object teaches us about the broader galaxy. Our Milky Way galaxy contains somewhere between 200 and 400 billion stars. Around most of those stars, planets formed. And during the formation of those planetary systems, material was ejected. Asteroids, comets, even planets, flung out into interstellar space by gravitational interactions. Over the galaxy's 13 billion-year history, the amount of material wandering through interstellar space has accumulated to staggering levels. Some estimates suggest there might be more mass in rogue planets and interstellar asteroids, comets, than there is in all the stars combined. Space between the stars isn't empty. It's filled with the debris of planetary formation, a cosmic diaspora of exiled worlds and fragments. These objects carry with them information about the systems they came from, chemical fingerprints, structural features, maybe even biological material, if they came from planets with life. They're like messages in bottles, thrown into the cosmic ocean, carrying news from distant shores. Until recently, we had no way to read these messages. They drifted past us unseen and unnoticed. But now we can detect them, study them, decode what they tell us about the galaxy's diversity. 3I Atlas, with all its strangeness, is teaching us that the galaxy is more diverse than we realized. It's showing us that our solar system's formation history, the specific sequence of events that led to the planets, and asteroids and comets we're familiar with, might not be typical. There might be many different pathways to planetary formation, many different outcomes, producing objects with properties we never expected. Dr. ʻOumuamua from the Space Telescope Science Institute studies the demographics of planetary systems and how they evolve over time. She's written extensively about what interstellar objects tell us about galactic evolution. In a paper published in January 2025, she argues, each interstellar object we detect is like a core sample from a different part of the galaxy's history. By studying enough of them, we can reconstruct the diversity of stellar and planetary environments across space and time. 3I Atlas is our third sample, and it's already showing us that the parameter space of possible outcomes is wider than we thought. Think about what that means. There might be categories of objects out there that we haven't even imagined yet because we've never encountered them. 3I Atlas might be representative of a whole class of unusual interstellar bodies that form under specific conditions, and we're just now discovering that such conditions exist. Or, and this is perhaps more profound, 3I Atlas might be truly unique, a 1 in a trillion oddity, the result of circumstances so rare and specific that we may never see another one like it. If that's the case, we're extraordinarily lucky to have detected it, and we should make the most of the opportunity. But there's another layer to this. Interstellar objects don't just tell us about where they came from. They also tell us about the journey they've taken. Remember, 3I Atlas has potentially been wandering through the galaxy for hundreds of millions of years. During that time, it's traveled through different regions of the galaxy, each with different properties. Near the galactic core, radiation levels are higher and star density is greater. In the spiral arms, there's more gas and dust. In the outer halo, it's quieter and emptier. An object's journey through these different environments would affect it. Cosmic ray exposure would vary depending on magnetic field strengths in different regions. Temperature would vary based on proximity to stars. There might even be collisions with interstellar dust grains, slowly eroding surfaces or adding new layers of material. Dr. Leslie Looney from the University of Illinois has been modeling interstellar object evolution during galactic travel. Her simulations show that the journey itself can significantly modify objects, sometimes in unexpected ways. She notes, "We tend to think of interstellar space as static and unchanging, but it's actually quite dynamic on long timescales. Objects traversing the galaxy are subjected to varying conditions that can alter their properties. Some of what we see in 3I Atlas might not reflect its original formation environment, but rather the cumulative effects of its long journey." This is a humbling realization. Even if we perfectly understand what 3I Atlas looks like now, we might never be able to fully reconstruct what it looked like when it first formed, because the intervening journey has overwritten or obscured the original features. It's like trying to read an ancient manuscript that's been copied and recopied by many scribes over centuries, with each scribe making small changes. The manuscript you're reading contains information about all those scribes and their eras, layered on top of the original text. Disentangling what's original from what's accumulated modification is enormously challenging. But here's where things get really interesting. If interstellar objects are modified by their journeys, then studying them doesn't just tell us about planetary formation. It tells us about the galaxy's structure and evolution too. The pattern of cosmic ray exposure on 3I Atlas, for instance, encodes information about the magnetic field environments it passed through. The surface weathering patterns might reflect encounters with dense molecular clouds. The thermal history might reveal how close it passed to various stars. In principle, if we could fully decode all these signatures, we could reconstruct the object's complete trajectory through the galaxy, seeing where it's been and what it's experienced. It's like forensic science on a galactic scale. We're nowhere near being able to do this yet. Our understanding is too incomplete, and our data is too limited. But that's the aspiration. Imagine a future where we've studied thousands of interstellar objects, developed sophisticated models of how journeys through different galactic environments affect different types of objects, and can use individual objects, like 3I Atlas, as probes of galactic structure and history. Interstellar objects would become not just curiosities, but tools for exploring the galaxy in ways that are otherwise impossible. After all, we can't visit the galactic core or the outer halo with spacecraft. The distances are too vast. But objects from those regions can visit us, carrying information about those distant places. Dr. Gregory Laughlin from Yale University describes this as passive galactic exploration. Rather than sending probes across the galaxy, which is far beyond our current capabilities, we can wait for the galaxy to send us probes in the form of interstellar objects. It's patient science, but potentially revolutionary. And here's one more profound implication. If material is constantly being exchanged between star systems via these interstellar wanderers, then the galaxy is more interconnected than we thought. Chemicals, organic molecules, maybe even biological material can travel from one star system to another. This process, sometimes called panspermia, could mean that life, if it arises in one place, might spread to others over long timescales. 3I Atlas itself shows organic molecules on its surface. If it had passed close to Earth during the early solar system's history, And if some of that material had been captured by Earth's gravity and survived atmospheric entry, those organic molecules would have been delivered to early Earth. Multiply that by billions of interstellar objects passing through billions of star systems over billions of years, and you start to see how the galaxy might be a connected ecosystem rather than isolated islands. This isn't science fiction. This is a serious hypothesis being explored by astrobiologists. And 3I Atlas, by showing us that interstellar objects can carry complex organic chemistry, is providing evidence that the material transfer necessary for panspermia actually occurs. I want to talk about something that doesn't often come up in science discussions, but that I think is crucial: the meaning of mystery itself. We live in an age where information is abundant. If you want to know something, almost anything, you can look it up instantly on your phone. We've become accustomed to having answers, to understanding things, to being able to explain the world around us. This is historically unprecedented. For most of human existence, mystery was the default state. People didn't know how the weather worked, where diseases came from, why the stars moved across the sky. Mystery was everywhere, and much of human culture, religion, mythology, philosophy, was about grappling with that mystery, finding meaning in the face of things that couldn't be explained. Science has been phenomenally successful at shrinking the domain of mystery. We understand weather now, and disease, and celestial mechanics. The universe has become increasingly transparent to human inquiry. And that's wonderful. That's progress. But 3I Atlas is reminding us that mystery still exists. Not the mystery of things we haven't gotten around to studying yet, but genuine, deep mystery. Phenomena that challenge our frameworks and resist explanation even when we direct enormous resources toward understanding them. And I think there's something valuable in that reminder. Living with mystery requires a kind of intellectual humility that's easy to lose when you're accustomed to having answers. It requires being comfortable with saying, "I don't know," and meaning it, not as a temporary state before you look something up, but as a potentially enduring condition. Dr. Marcelu Gleiser, a theoretical physicist and philosopher from Dartmouth College, has written about what he calls the island of knowledge. He describes human knowledge as an island in an ocean of ignorance. As the island grows, as we learn more, the shoreline where knowledge meets mystery actually gets longer, not shorter. Every answer generates new questions. The more we know, the more we realize we don't know. 3I Atlas is a perfect example of this. Before we detected it, we had a nice, tidy theory of interstellar objects based on ʻOumuamua and Borisov. Now we know more. We've added a third data point, but we understand less than we did before because that new data doesn't fit the pattern we thought we'd identified. This is frustrating if you think science is about accumulating certainty. But it's exciting if you think science is about exploring the unknown. There's also something humbling about being confronted with phenomena we can't explain. It reminds us that reality doesn't care about our theories or our comfort. The universe is under no obligation to be comprehensible to human minds. The fact that we've been successful in understanding as much as we have is extraordinary and maybe even a bit lucky. Dr. Jana Levin, a cosmologist and philosopher at Barnard College, said in a recent podcast, "I think 3I Atlas is good for science because it's making us uncomfortable. We're being forced to sit with uncertainty and admit that our models might be wrong. That's healthy. Science works best when it maintains that kind of humble, open stance toward reality rather than becoming attached to its own theories." But there's a deeper philosophical question here too. What does it mean for something to be explainable? We assume that everything has a cause, a mechanism, a story that makes sense if we could just figure it out. But is that assumption justified? Is the universe fundamentally comprehensible? Or are there aspects of reality that might be inherently beyond human understanding? This isn't mysticism. It's a legitimate question about the relationship between the structure of reality and the structure of human cognition. Our brains evolved to navigate a specific environment, to solve specific problems related to survival and reproduction. The fact that these brains also happen to be capable of understanding quantum mechanics and general relativity is remarkable, and not something evolution specifically selected for. But maybe there are limits. Maybe there are aspects of reality that can't be encoded in the kind of mathematical models and verbal explanations that human minds naturally create. 3I Atlas might be giving us a glimpse of those limits. Maybe the reason its properties seem contradictory and inexplicable isn't because we haven't found the right theory yet, but because the phenomena we're observing emerges from processes that are fundamentally complex in ways that resist simple explanation. This isn't a comfortable thought for scientists, who are trained to believe that persistence and cleverness can eventually crack any problem. But it might be true nonetheless. Or, and here's a more optimistic possibility, maybe we just need to think differently. Maybe the framework we're using, based on studying solar system objects, is the wrong framework for understanding interstellar objects. Maybe we need entirely new concepts, new mathematical tools, new ways of modeling reality to make sense of what we're seeing. History shows that this happens. Newtonian mechanics worked perfectly for everything humans had observed for centuries. Then we started observing things moving very fast or experiencing very strong gravity, and Newtonian mechanics failed. We needed Einstein's relativity, a completely new framework that reconceptualized space and time themselves. Similarly, classical physics worked great until we started probing atomic scales. Then we needed quantum mechanics, which required accepting seemingly absurd ideas like particles being in multiple places at once and observation affecting reality. Maybe interstellar object physics will require a similar conceptual leap, not as dramatic as relativity or quantum mechanics, but still significant enough that we can't quite see it from where we currently stand. And that's exciting. We might be on the verge of a conceptual breakthrough, a new way of thinking about small bodies in space that will suddenly make all the puzzling data click into place. Or we might not. We might study 3I Atlas and all future interstellar objects and never quite figure them out, remaining perpetually confused by observations that don't quite fit our theories. Either way, the journey is valuable. The process of grappling with mystery, of pushing at the boundaries of understanding, of refusing to give up even when answers remain elusive, that's what science is really about. Dr. Lisa Kaltenegger from Cornell University, who searches for signs of life on exoplanets, said something beautiful in an interview. Every scientist dreams of finding something that doesn't make sense, something that breaks the rules, because that's where discovery happens. 3I Atlas is a gift to the scientific community. It's given us a genuine mystery to solve. Whether we succeed or fail in solving it, we'll learn something profound in the attempt. As we approach the end of this journey together, I want to zoom out to the biggest picture possible and think about what 3I Atlas means for humanity's future. Right now, we're a species confined to one planet orbiting one star. We've sent spacecraft to every planet in our solar system, landed rovers on Mars, and even sent a few probes beyond the solar system's edge into interstellar space. But those probes, Voyagers 1 and 2, New Horizons, and a couple others, are traveling so slowly that they won't reach even the nearest stars for tens of thousands of years. Interstellar travel, meaning sending humans or even sophisticated probes to other star systems within reasonable timeframes, remains firmly in the realm of future technology. It might happen in a century, or a millennium, or never. But while we can't yet go to the stars are coming to us in the form of interstellar objects like 3I Atlas. These objects are messengers from beyond, carrying information about other worlds, other systems, other corners of the galaxy. Studying them is our first real taste of interstellar exploration, our first opportunity to examine matter that originated around other stars. And 3I Atlas specifically is showing us just how alien those other systems might be. The object's strange properties remind us that planets and stars elsewhere might be fundamentally different from what we're used to, formed through different processes, evolving in different ways. This has implications for how we think about searching for life beyond Earth. We tend to look for life in places similar to Earth, planets orbiting sun-like, stars at the right distance for liquid water to exist. This makes sense, given that Earth is our only example of a life-bearing world. But what if life can emerge in environments we haven't considered? What if some of the strange processes that created 3I Atlas also operate on planets, creating exotic conditions where exotic forms of life might thrive? Dr. Dimitar Sasolov from Harvard University, who studies exoplanet habitability, argues 3I Atlas is expanding our sense of what's possible in the universe. If we're surprised by the properties of one interstellar asteroid, imagine how surprised we might be by the full diversity of exoplanets. We need to be humble and open-minded in our search for life, ready to find biology that doesn't look anything like what we know. But there's another angle to this. If humanity eventually becomes an interstellar species, if we develop the technology to travel between stars, we'll encounter interstellar objects ourselves during those journeys. Understanding them, knowing what to expect, recognizing hazards and opportunities will be crucial. 3I Atlas, with its unexpected acceleration and mysterious properties, shows us that interstellar space might be more hazardous and unpredictable than we thought. An object that appears to be an inert asteroid might have unexpected internal dynamics or magnetic fields or structural instabilities that could pose risks to spacecraft. Conversely, interstellar objects might be resources. They're full of water ice, organic molecules, and minerals. Future spacecraft on long interstellar journeys might stop at these objects to refuel, to mine resources, to take shelter from cosmic radiation. There's even been serious discussion about intercepting interstellar objects and pushing them into orbit around Earth or another planet, essentially capturing them for study and resource extraction. This is technically feasible with sufficiently advanced propulsion systems, though well beyond our current capabilities. Dr. Andreas Eng from the Initiative for Interstellar Studies has studied the concept of intercepting and redirecting interstellar objects. He notes, these objects represent free delivery of material from other star systems. Rather than waiting for them to pass by, we could capture them. An object like 3I Atlas could contain trillions of dollars worth of resources if we could bring it back to Earth orbit. And the scientific value is priceless. But let's think even more long-term. What if interstellar objects are more than just resources or scientific curiosities? What if they're part of a natural system of material exchange between star systems that we're only beginning to recognize? I mentioned panspermia earlier, the idea that life might spread between worlds on meteors or other natural objects. Interstellar objects take this concept to a galactic scale. If organic molecules, and potentially even microbial life, can survive the journey between stars on objects like 3I Atlas, then life might be spreading throughout the galaxy through natural processes. No technology required. This would mean that life on Earth might have interstellar ancestry. The chemical building blocks that led to the origin of life on our planet might have been delivered by an ancient interstellar object similar to 3I Atlas billions of years ago. And if life can spread this way naturally, then advanced civilizations could potentially spread deliberately, sending not just information or machines, but biological material, seeds, spores, DNA, throughout the galaxy on slow but inevitable trajectories. This connects to a concept in astrobiology called directed panspermia, proposed by Francis Crick and others. The idea that life on Earth might have been intentionally seeded by an advanced civilization. While there's no evidence for this, and it remains highly speculative, 3I Atlas shows us that the transport mechanism is at least plausible. Objects can travel between stars carrying organic chemistry intact. Now, I want to be clear. I'm not suggesting 3i Atlas is artificial or was sent by aliens. I'm simply pointing out that the existence of interstellar objects and their ability to carry complex chemistry opens up possibilities for how life, intelligence, and even civilization might spread through the galaxy. Dr. Claudio Grimaldi from the Swiss Federal Institute of Technology has written about what he calls the galactic internet, the idea that advanced civilizations might communicate not by radio signals, but by physically sending objects between stars using interstellar wanderers as message bottles. Such a communication system would be slow. Messages would take millions of years to arrive, but it would be persistent. Physical objects aren't subject to the degradation that affects radio signals over interstellar distances. He proposes that if we really want to search for messages from extraterrestrial intelligence, we should carefully examine every interstellar object we detect, not because we expect them to be spacecraft, but because they might carry information encoded in their structure, their composition, or even in artificial molecules designed to be recognizable. This is speculative, but it's not ridiculous. And 3i Atlas's anomalous properties make you wonder, even if just for a moment, what if? What if one of these interstellar visitors, maybe not 3i Atlas, but some future one, turns out to carry clear evidence of artificial modification or embedded information? What would that mean for humanity? It would be the most profound discovery in history, instantly answering one of humanity's oldest questions. Are we alone? It would tell us that intelligence has arisen elsewhere, that civilization can persist long enough to engage in interstellar projects, and that we're part of a larger cosmic community. Even if 3i Atlas turns out to be completely natural, studying it and objects like it is preparing us for that possible future. We're developing the tools, the techniques, and the mindset needed to recognize something truly anomalous if we ever encounter it. And more fundamentally, engaging with the mystery of 3i Atlas, grappling with phenomena we don't understand, being humbled by the universe's complexity, learning to sit comfortably with uncertainty. These are skills humanity needs as we venture further into the cosmos. The universe is stranger than we imagined, and probably stranger than we can imagine. Objects like 3i Atlas are teaching us that lesson. And if we're wise, we'll carry that lesson with us as we become an interstellar species ourselves.